Okay.
Okay, it's good. Okay, so what we did was chapter 30, Galaxies and the Universe. Esteban will be presenting section 1, I'll be doing section 2, and we will both be doing section 3. Section 1 is on the Milky Way galaxy, section 2 is on other galaxies in the universe, and section 3 is in cosmology. Esteban?
Alright, can you click please? So for the first thing that we're doing is called variable stars, and thank you. Variables are stars that have a period of pulsation which is about 1.5 hours or 1.2 days. The other type of stars is Cepheid variables. Sorry, this looks so bad. But however, those are like longer. They can have about 100 days or 10 days for that. The galactic center, which is what astronomers are trying to discover, which is the center of a galaxy, for example, the Milky Way galaxy, discovering what's in the middle of it, if it's huge amounts of planets, what's in the middle of it. Can you, next page, please? The halo is an area where globular clusters are found. Spiral arms or hydrogen atoms make up most of the spiral arms. Nuclear bulge or bar. Astronomers technically don't know what's in the middle of the Milky Way, meaning if it's a bar or a barge. But for now, scientists have said that it's probably a spiral barred galaxy for now.
And down here you can see the different areas. Like right here is the bulge, and around here in the halo is where globular clusters are, and that's where the variable stars are found.
Right, next. Different ages. What this section is also explaining is also about the different ages of the stars and how some of them can be millions of years old, others can be a lot younger, others can be a lot older. Spiral density wave. Spiral density wave is explaining about the density of the spiral that we have in our galaxy, how dense it is, what is in it. Like, we already know what is in like hydrogen, well, how dense it is in the galaxy. Next. So for this one, for this section 2, I'm going to pass it to Kevin.
Okay, thank you. So section 2 is on other galaxies inside of the universe. And something about galaxies that people may not know is that galaxies can be used as time capsules from the past. Because the light from them is billions and billions of light years away, and so it takes light millions and billions of years to get to the Earth from a secular point of view, that is. And so by looking back into the history of the cosmos, by looking at galaxies from super far away, you can see what the universe was like at the beginning, again from a secular point of view. And galaxies can also shed light on the future of our galaxy and what will happen to our galaxy. Like in this picture, you can see this is the Mice Tail galaxy. It's actually two separate galaxies that have collided and have gone past each other. And that's exactly what's going to happen to our Milky Way galaxy and the Andromeda galaxy. And the Andromeda galaxy is the closest galaxy to our own, besides the large and small Magellanic Clouds. It's the largest spiral big galaxy that we know. Next. So the properties of galaxies. There's different properties of the galaxies, like the age, the mass of it, the apparent magnitude, and the distance. The apparent magnitude is not the absolute magnitude, because the absolute magnitude of a galaxy would be absolutely gigantic. But the apparent magnitude is a lot smaller than like most stars that we see, because they're so far away. And we can see the age of them by looking at the different kind of stars that they have in them. Like blue stars are generally younger stars, and red stars are most always older stars. And there's different classifications of galaxies. There is the disk-like galaxies, there are elliptical galaxies, and there are irregular galaxies. Disk-like galaxies are like spiral galaxies, like our own. Elliptical galaxies are like big, giant clusters of stars. They don't have much of a shape besides a giant sphere in intergalactic space. And irregular galaxies is what happens when galaxies collide, like I was showing in the minus tail galaxy. Next. Okay. Section 2. Groups and clusters of galaxies. The local group, which is what our galaxy is made of, is the Milky Way's neighborhood. And we know of 40 other galaxies that are within our local group. That's what we call it. And so there are large clusters. Large clusters are a lot larger than our local group. They can be 50 to 30 million light years in diameter. And they have hundreds of thousands of galaxies. It's quite amazing. And then there are masses of clusters. There are superclusters, which are even more gigantic. They are absolutely humongous. And so the expanding universe. Edwin Hubble is the man that discovered the thing, the law of Hubble's law and redshift in galaxies. And he's the person that has mainly led the discovery of the expanding universe theory. And so what the implications of redshift imply that since everything has a redshift to it, all the galaxies are expanding away from each other, and everything is moving away. And so that by using that, astronomers have concluded that if everything's moving away from something, it all must have come from something. So everything must have been together at one single point, and that is the Big Bang Theory. Next. All right. And so active galaxies, there are radio galaxies, which are galaxies that are full of radioactive things. They are very bright, they are like big elliptical galaxies, and they emit lots of wavelengths of energy. And quasars. Quasars are black holes that are spewing out particles and matter and just everything. Because the black hole, this is not an actual picture of a quasar, but this is an artist thought of it. And this is what it would be. It would be a giant black hole at the center of a large disk of matter, gas, and just everything. And then as everything is sucked in, the black hole cannot suck everything in at once. And so some of it just spews out of the side, and it goes away. And section 2,
All right, I'm going to come in. So for section 3, cosmology and the origins of the universe, people have concluded a theory that everything started from a very dense one object, a very dense thing, so dense that it exploded. And as it exploded, it expanded. As it expanded, creating galaxies and everything that we have in our universe, or in any way that we have that's possibly visible in space. Next one, please. For the possible expansions, they actually have 3. You want to go with it?
Yeah, All right. So there are 3 possible outcomes. There is the open universe, the closed universe, and the flat universe. You want to talk about open universe?
Sure. Open universe is when they say like the expansion is unlimited. It will always expand and never stop. For closed universe, oh, you want to go on?
Yeah. Closed universe is when when there's a certain amount of matter one moment, please, let me find it. The critical density, which is what is down there. If the universe has this critical density, which is 6 times 10 to the power of negative 27 kilograms divided by meters cubed, then the universe will be a closed universe, and it'll all come apart, which is what we're seeing now, and then it will all contract together back into that single point. But scientists have not been able to discover, even with the calculations of dark matter, which we'll talk about later, we've not been able to account for that specific mass.
Okay, so for flat universes is a little bit of both technically. It's what's saying is that the universe is still expanding infinitely, but gravity is somehow giving it so much critical density, but not as much as having a closed universe. It's having so much critical density as it's slowing down in speed, which makes it look like it's stopped, but technically it's still going. Right? You got it? Right. You want to have that? Right. So for this one, the cosmetic radiation background is saying that as they say, like the Big Bang exploded, radiation was there. So as they say, they're trying to map out a timeline explaining about when, if it's true that the Big Bang Theory actually happened, and what happened to it. How did it expand so big?
The cosmic background radiation is what scientists believe to be the biggest evidence for the Big Bang, because they say that when it happened, that it all expanded, and this is what is left over. So they point to this as the biggest point for the Big Bang. Thanks. Go.
Dark matter isn't like a big such a thing. It's there, but what dark matter is, it's saying that we technically can't see dark matter, but we can actually see its uses. Actually, we know that dark matter has some sort of energy that is some sort of negative energy in space that actually shows that it's real.
Like we can see its effects,
yeah,
but we're not able to observe it.
It's like air. You can not technically see its physical form, but you can see like what air does. I got nothing else.
But it's a lot more complex.
It's a lot more complicated. We can't go that far for that.
The book didn't spend too much time on
yeah.
Next.
Okay. All right.
So the interest in the topic. So do you want to go first?
Yeah, I'll go first. What interests me in this topic specifically is, first of all, I love astronomy, cosmology, everything. I love how this isn't the only planet we can technically live in. There are millions upon millions of galaxies, expanding universes, and so much more. So it kind of intrigues me and actually fascinates me of what is beyond our Milky Way galaxy, what's beyond us. That's it.
And my interest is very similar to this. I love the feeling of knowing that there's like everything around us, like we can see like that the stars in the night sky, and that star has planets revolving around it just like ours. And then if say there was something over there looking towards our star, they would see that and be thinking about how there's planets revolving around it and everything. And it just amazes me how small we are in such a gigantic, huge world.
Yeah. So for current events, what I found out was they found out a galaxy, which they kind of named it the dinosaur egg, which is not literally a dinosaur egg, I'm just going to tell you that. They call it the dinosaur egg because it's one of the oldest ones they found.
It's the oldest galaxy that has ever been observed.
Yeah, so it's like prehistoric age, for example. Like they know it's like one of the oldest ones, and they want to know what else it has. Since we're up in time, I'm just going to say the questions and answers since we have to cut short on time. The first question is, what type of galaxy is the Milky Way? Barred spiral galaxy, or irregular galaxies? It's A, barred spiral galaxies. As for the next one is, what are radio galaxies? Is it A, galaxies that have radio station? Is it B, extremely luminous elliptical galaxies? Or is it C, extreme luminous spiral galaxies? It's B, extremely luminous elliptical galaxies. As for the third one is, which law shows that the universe is expanding? Hubble's law, Kepler's